All right, so welcome back for part 3. We're doing some more quotient rule problems. Again, our rules are to find the derivative for, and in this case, we got this guy. All right. I'm hoping you're seeing what I'm saying. I'm hoping that you're looking at this and just taking a moment instead of just going fraction quotient rule and jumping right in. I'm hoping that you're going to notice that the denominator, I wanted the highlighter, that the denominator is a monomial, one term, and the denominator does not contain a variable, which means that we could rewrite this as 1/6 times x squared plus 3x. And when I rewrite it as that, I no longer need the quotient rule. I don't have to worry about lows and highs and derivatives of numerators and derivatives of denominators and squaring denominators. I can just simply work this problem out without needing any of that. Okay? This is a coefficient, so it is going to be the coefficient of the entire derivative. This is an f. This is a g. The derivative of f plus g is just going to be f prime. Derivative first, 2x plus g prime. And then if we distribute that 1/6 back in, I would get dy dx is going to be 1/3 x plus 1/2. And I'm done. Now, had I used the quotient rule and had I been able to use the quotient rule correctly, I would have ended up with this same result. It just would have taken about 4 times as long. Okay? All right, how about this one? It's a fraction. Does that mean I need the quotient rule? And again, the answer is no. While this is a fraction, I do not need the quotient rule because I can rewrite this as 9/5 x to the negative 2. So when I'm taking derivatives and I see a fraction, my first response shouldn't be, I have to use the quotient rule. My first response should always be, do I need to use the quotient rule? And here I don't. So I can get that the dy dx is going to be the coefficient, 9/5, multiplied by the derivative of x to the negative 2. So that's going to be a negative 2x to the negative 3. Remember, the exponent drops down in front, becomes that coefficient, and then we subtract 1 from the exponent. So then cleaning that up a little bit, looks like I've got negative 18 over 5x cubed. And there's my derivative, dy dx. Okay? All right, how about this one? Do I need the quotient rule? I see a quotient, clearly. There is a quotient here. But do I need the quotient rule? Okay, I gave you a second to think about it. The answer is no, I don't. Since my denominator is a monomial, I can rip this thing apart and simplify it. And when I rip this thing apart, I get 3x squared over x plus 2 root x over x, which then simplifies to 3x plus 2x to the negative 1/2. 3x squared over x simplifies to 3x. 2 root x over x simplifies to 2 times x to the negative 1/2. And now I can take the derivative, g prime of x. This is just 2 terms being added together, so it's the derivative of the first term, 3, plus the derivative of the second term, which is going to be 2 times negative 1/2 times x to the negative 3/2. Remember, we're subtracting 1 from that exponent. Cleaning that up a little bit, I get that g prime of x is equal to 3 minus x to the negative 3/2. Or if you prefer, we could rewrite that and say that that is g prime of x, and that is equal to 3 minus 1 over x square root x. Remember, x to the 3/2 means the square root of x cubed, but the square root of x cubed is x root x. The negative exponent just puts it in the denominator. Okay, and there's my derivative. Now, if you feel the need, you could get a common denominator and put that back together and make that into a single fraction, but there's no need to. All right, so here we go. I have another quotient. I see that there's a division. There is a quotient here. Do I need the quotient rule? The answer is yes. Since my denominator is a binomial, and I cannot divide this thing out, my numerator is a monomial, it won't divide out, then I'm going to require the quotient rule here. Okay? So then quotient rule. So u is my numerator, u is e to the x, u prime is also e to the x. V is my denominator, that's 1 minus e to the x. V prime is going to be negative e to the x. And then putting it all together, I'm going to get then that dy dx is equal to, and in case you've forgotten it, it is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Okay? Putting the appropriate pieces and parts where they belong, I'm going to get then that dy dx is equal to v 1 minus e to the x times u prime times e to the x minus u e to the x times v prime, that's a negative e to the x, all divided by v, that's 1 minus e to the x squared. Should probably clean this up a little bit, so I'll do some distribution and whatnot on that numerator and clean this thing up. That's going to give me then that dy dx, derivative y with respect to x, distribute e to the x times 1 is e to the x. E to the x times negative e to the x is negative e to the 2x. Okay, remember, same base, add the exponents. Over here I've got negative e to the x times negative e to the x. That's going to make it positive e to the 2x. And then my denominator is 1 minus e to the x squared. What's going to happen here with those two terms? Looks like they're going to cancel. And we get then in the end that my dy dx will be e to the x over 1 minus e to the x squared. And I'm done. So I'm using the quotient rule. Okay. All right, so we've done a lot where it's just operational. Let's see if we can take a look at a couple that are, how you want to call this, maybe conceptual. All right. So here I have a graph, and I have on that graph two functions. I have the function f, and I have the function g. G is the green function, f is the red function. We are told that p is f times g, and q is f divided by g. Okay? In part A, they're going to ask me to find p prime of 2. All right, since I have a graph, that means that I'm interpreting the value of the derivative to be the slope of the graph. Since I have a graph, I'm interpreting the value of the derivative to be the slope of the graph. Challenge is, I don't have a graph of p. I have graphs of f and g. So how am I going to find p prime of 2 if I have graphs of f and g? Okay. Well, here's the logic. If I know what p is in terms of f and g, I should be able to find p prime in terms of f and g. That is, if p of x is equal to f of x times g of x, then p prime of x should just be f of x times g prime of x plus g of x times f prime of x. I'm just making use of the product rule, which means then that p prime of 2 should be f of 2 times g prime of 2 plus g of 2 times f prime of 2. And now I should be able to figure out p prime of 2 because I have all the information I need over here for f's and g's on this graph. All right, so from left to right, working my way through this problem, what is f of 2? Well, here's 2. There's the function f, so it looks like f of 2 is 3, times g prime of 2. Okay, so let me get rid of this. G prime of 2. here's 2. There's the g function. But g prime of 2 doesn't ask me what the y value is. It asks me what's the slope there. But it looks like this is a line segment. It looks like the run is 2 for a rise of 1. So I would say that g prime is 1/2. Plus, and I'll clean this up, g of 2. All right, g of 2, g of 2, g of 2, g of 2. Here's 2. There's g. G of 2 is 2. Times, okay, let me clean this up, f prime of 2. There's 2. There's f, but I don't want this. I want the slope there. And it looks to me like that would be a horizontal tangent line. And so the tangent line there being horizontal, which means would be the slope would be 0. And so then doing a little bit of arithmetic, I get that this is equal to 3/2, or that p prime of 2 is 3/2. 3 times 1/2 is 3/2. 2 times 0 is clearly 0. And so we got our 3/2. Okay. Now we're going to use that same kind of logic to figure out q of 7, because I don't have a graph for q, I have a graph for f's and g's. But if q of x is defined to be f of x divided by g of x, then what would q prime be? Well, it looks like a quotient rule problem to me. And hopefully by now you've caught on that p was product, q was quotient. Okay? And so this will be g of x times f prime of x minus f of x times g prime of x divided by g of x squared. Or, for our problem, q prime of 7 is going to be g of 7 times f prime of 7 minus f of 7 times g prime of 7 divided by g of 7 squared. Okay. Now I just need to use this graph to find all those things. Okay. All right, here's 7, because everything is centering on 7. Working through the numerator. So q prime of 7 is going to be g of 7. G of 7, there's the g graph. There's g of 7. G of 7 is 1. Times f prime of 7. There's the f graph. F prime, though, I don't want the y value, I want the slope there. Well, it looks like that's a line segment, and it looks like if we draw in the triangle, that's a run of 4 and a rise of 1. So then the slope there would be 1/4 rise over run minus, let me clean this up a little bit, don't need all this gobbledygook on my graph. Okay. Minus f of 7, so there's 7. There's f of 7, looks like 5, times g prime of 7. Okay, so there's the graph, but I don't want g of 7. I don't want the y value. I want the slope there. It looks like we got a run of 3 and a rise of -2. So then the slope would be -2/3. All divided by, and what are we dividing this thing by? Oh yeah, that's right. We're dividing by g of 7 squared. But g of 7 was 1, so 1 squared. So now I got to clean this up a little bit, and so I get that q prime of 7 divided by 1 is simple. So it's 1/4 minus, well, it's actually going to be plus because a -5 times a -2, so plus 10/3. And so what's 1/4 plus 10/3? And I hope that you're not reaching for your calculator. You should be able to turn these into fractions pretty much in your head. Okay, this is going to be common denominator, at least common multiple of 4 and 3 is 12. So that's going to be 3/12, and that's going to be 40/12. And 3/12 plus 40/12 is 43/12. So q prime of 7 is 43/12. And that brings us to 15 minutes. So I'm going to close this video here and come back and make another video. And that last one should do the rest of the derivatives. That is the derivatives of the rest of those trigonometric functions, and then some higher order derivatives. Okay, so I'll see you back here for the next part of the video.